So Ankit, please.
So thanks a lot, Stylight, for and Altros for inviting me. I'm Ankit Bahuguna. I work for Cliqz as a software engineer, and today I'll present you an overview about TensorFlow. A bit of information about me. I'm actually working at Cliqz as a search engineer, where we are building a web-scale search engine for the German community. The areas which I'm really interested in are like information retrieval, machine learning, deep learning, and natural language processing. I completed my master's in TU Munich last year, and I have a work experience at TUM, LMU, Teradata, and IT Bombay. And I'm also representing Mozilla since the last 4 years. And you can actually write to me at CodeKey, which is my Twitter handle. So a bit more about Cliqz. We are based in Munich. It's largely owned by Hubert Buddha Media. We have an international team, which is like 27 countries with 90 experts in it. And we are combining data, search, and browsers together to give a seamless integration of a new experience of internet itself. And we have Android and iOS apps, and the web browser is like based on Firefox. We have a Cliqz extension as well, which runs on Firefox with anti-tracking enabled, which is quite a huge thing in Germany. So go through Cliqz and tell us how we are working on. So the outline today. So first, I'll just start with what TensorFlow really is and what it brings to the table. What are the mechanics behind it? And what is this thing called TensorBoard, which allows you to visualize your learning. There are some demos that I have prepared, some benchmarks which have been contributed by the community about how this stacks with other deep learning toolkits, and some of the applications that we have. And at last, I can have Q&A. So TensorFlow is, as we all know, it's like an open source software library by Google. It runs on both the single machine and distributed implementation. That's what the paper says. And with multiple devices like CPU or GPU. The code is itself written in C++ with Python API wrappers around it. The latest stable release is like 0.71, which was released around 10 days back. And the license is Apache 2 open source. And the website is tensorflow.org. So what is the usage of TensorFlow? So one of the questions in the fireside chat was about NLP. Since I'm an NLP person, so I can probably answer it. So one of the key things that was in the news by Google was RankBrain, which is the information retrieval engine behind Google.com, which is supposed to be the third most important signal for them. So that runs sort of the TensorFlow backend, where they're using deep neural networks to solve or understand user queries. The other thing is the inception image classification model, which probably people know about. That's the 2014 model, which won the ImageNet competition. That is also running, all the computer vision research goes on in Google with TensorFlow. They have a blog post on Google Research about Smart Reply, which is like an LSTM-based model, which automatically generates replies to your emails, the emails that come, and it's also in your phone. So in the Android, you can actually see how it works. There are also some collaboration with Stanford for drug discovery, where they can actually like identify strands of drugs, and that also uses deep neural networks. Again, collaboration by Google and Stanford. And the last one is an on-device computer vision for OCR, which you probably might have used already, which is the Google Translate app, which you can actually just take a picture, and in the real time, you can just transcribe or translate what that picture, or the text inside the picture. It does something called optical character recognition, or OCR, and that also uses TensorFlow. So how is it different from all? So as we know, we talk a lot about like what that it can run on several devices. What it actually means is like it can not only run on your Intel CPUs, but also on ARM architectures. And most of your mobile devices are ARM enabled. And the reason behind it is like they don't use BLAS at C++ level. They're using something called Eigen, which is compatible to ARM. So you can actually then deploy this particular model that you train on, say, there's a research team in your office which is researching on some models, and then you want to just put that same model in the production. It's really simple because you don't have to give it to an engineer to optimize, to write a production level code, which is actually the case with machine learning, why people are not able to like bring a production ready model so that people use it. The other thing that TensorFlow actually has is multi-GPU training, which like if you have several GPUs, like if you have used AWS infrastructure, the G2 machines, which actually allow you to have like 4 GPU cards at the same time, you can actually utilize all those 4 at the same time and use it in the learning. But Microsoft, which has this thing called CNTK, they claim that they use something called 1-bit SGD, which is much faster, and they claim to be the fastest in this league. And yeah, they have some numbers to claim as well. It's very clean and modular architecture. If you look at the images, it's like the CPUs, GPUs on the lower level are your devices. The yellow layer is the TensorFlow layer. It's the way the library is written. And at the top is the API wrappers that are around it. So if you want to add like a new wrapper, say in Rust or Go, you can probably use that as well. So it becomes very easy for new developers or new languages to abstract that particular model out of it. So coming to the mechanics. So a TensorFlow computation is like a data flow computation, which can be represented as a directed graph, and a graph has nodes. The graph actually represents this computation, which actually provisions the nodes for maintaining and updating states. And it has some branching and looping support. The node actually represents some sort of an operation. An operation could be like an add, multiply, like a matrix multiply. The tensor is some sort of an arbitrary dimensional array, which is like n-dimensional array, which you can think about as like between two nodes, there are edges, and on the edges there are weights. So tensors define that, and they are mutable, so you can change them. There are certain control dependencies, like if you want to go from node 1 to node 2, what happens is like you want to say, okay, there has to be some task which has to finish, or I want to just regulate this task. You can like define that in the control dependencies. Then there is the operation, which is like an abstract computation, like again, add, matrix, multiply. The operation can have attributes. Like at the graph construction time, you have to instantiate that node, say instantiate all the variables. So this happens like only once. And later I'll show in the demos like how this works. The kernel is actually a particular implementation of that particular operation. So if I want to do matrix multiplication on CPU and on GPUs, probably the code could be different. The way it handles memory would be different. So you can actually write kernels for both of them. And as we see in the latest releases, that there are new operations that are being written, like fast Fourier transforms, etc. The whole TensorFlow system is sort of managed by something called a session. The session is what initializes your TensorFlow system to work. When you do session.extend, you can actually have one session, say you have a part of a graph computation, and you want to add some more stuff to it. You can do that session.extend to get like some more information out of your already running system. The second thing is session.run. So when you create a session, you want it to run. That is, say, training a model or evaluating a model or like testing on your set. That you can then use using session.run. The variable is called a special operation. All this data comes from the white paper itself. So these variables are those which can actually you can actually change, and this actually helps you to do this iterations of several training steps. So when you want a model to run 100 times, you want that state to change and some state to actually remain. This thing can be done using variables. And they have special operations within that operation that is called assign, like say your counter equals to something, and counter addition or increments. So that thing is like stored in variables. The way it is implemented in the backend, it's like they have a single this master and worker process architecture, where say if you're running it on a single machine, it's the image on the left. You have a client which actually accesses a master, and that has access to all the worker nodes. The worker itself has these several devices that are mapped to it. Now, devices are like CPUs and GPUs, but there is like a registration mechanism, which they claim in the paper, that you can actually like say if you want to have a new device, say a new chip which just runs a particular computation very fast, you can actually like register that, and even that also like takes place. So that's pretty cool. The other thing is the distributed implementation, which was the reason the paper was so highlighted about, which right now is not there in production or in the master branch, is you can actually like have the same worker processes across several different systems in a cluster. So that will actually allow you to do some sort of a data like you can actually divide the data set, and you can actually like train these models on several CPUs, just like what MapReduce does. And you can utilize the cluster itself for training. And this is pretty useful if you are like dealing with a lot of data, say terabytes of data, and you really want to learn with several iterations and like several models altogether. So the devices itself are like named like this, like it's called job, localhost, device CPU, or some worker with a particular task and the GPU. That's how they define it in the code. The tensors are again a typed multi-dimensional array. They are typed, so they support like integers, signed and unsigned, IEEE floats, double, so all these complex types and string types. So you can actually like store these many sort of data items in it. And the beauty about this is that since the whole kernels are actually provided by Google, at least for the default algorithms, you can actually not think about what happens to the GPU memory, which is very scarce, or what happens to CPU memory. They are like handled all together, so it's pretty easy to start with. So this is like one piece of small TensorFlow code, again from the paper. So on the left side, we see the code. On the right side, we have something called the computation graph, which the code generates inherently. We start with like an import, TensorFlow as TF, and then we start variables. Initialization of B stands for bias, and W stands for weight. And X is like a single placeholder, which is your input. You can create a placeholder which says, okay, this needs to be fed consistently. Your tf.0 is 100, means I want an array of 100 dimensions with zeros in it. The second tf.random uniform. These functions are all defined in TensorFlow. Again, a 784 by 100 with like a uniform distribution between -1 and 1. Then we also have these things called rectified linear units, which are quite famous in connets sort of area, where you can actually have this nn.relu, that's a function, and you can define this wx plus b computation, which is your sort of what you use in this linear regression. And you can have your cost function, which is the loss function, based on some function of this particular ReLU unit. So it's same as any neural network. You have some inputs, you have some computation, you have some outputs, but you want to minimize the loss. And to do that, what you have to do is like, you need to define this loss function. And to run this several iterations into it, you define something called a step, which runs it, say, like this line for step in X range, that runs it 10 times. With an input, again, you feed that input, whatever input that you have. So you have images or text as some n-dimensional arrays. Like here you have 100 dimensions. And then you do a run. So when you do an s.run, the entire thing gets initialized. And when you like write the code, you have to like initialize it. And you can provide this input vector. And C is your cost function. So based on your C, either you maximize or minimize that. It will run it n times. And then the last line will just print it. What computer, like the system itself, understands it is like a graph formulation of the thing. On the left side, we have W and X as the input to a math multiplication, that is WX. And then you do an addition to add the bias. And then an ReLU layer is there to get the output on the cost function. So this is how the system actually understands this code, this piece of code. We'll see in the example how it actually works. There is something called TensorBoard, where we actually can visualize learning. Often what we see is like when we are running a neural network and it runs over, say, several days, you want to find out whether your biases are is it converging or diverging, or is it really what you are looking at. And this is particularly good because, say, if you are really training on pretty high data sets, especially in size, then you probably want to know whether you are actually investing in the right computation power or not. So they have this thing called TensorBoard, which could say you can actually plot your losses, your biases, your weights. I have a demo about it, which you can use. And there are these NN biases. These are some these pictures, again, biases, plotting against time, some sort of time series data, what happens like in biasing or gradients or weights, how they change over time. So that you can actually say. And in the first figure, you can see the accuracy or whatever. This is the cross entropy, actually. That it decreases over time, which actually tells, like, given a neural network, whatever your outputs are, how well are they performing against the existing test set or the set that you already have. They have something called graph visualization. Again, as I said, there are these nodes that you can actually see that people can just zoom in or zoom out to. So given, say you have a 2-layer convolutional neural network and you want to find out what actually you have coded, or what kind of layers architecture that you have. Especially if your model is pretty complex, you can actually just look at it. You can't really tune anything, but you can just look at how your architecture is. You can save it. You can generate a lot of other information which can be useful for like good visualization of how it is performing. It also runs on like a serialized set of data. So as soon as your computation is running it, you can actually create a graph which runs like in real time, which is pretty good. This is one example of a CNN which uses like 2 or 3 layers, and it uses 2 convolutional neural layers, con1 and con2 at each level, and then it actually like feeds into a softmax linear layer, and then a softmax layer at the top, and at the top we have a moving average. So just by looking into the graph itself, you can see how the convolutional neural network is actually like moving, and it's quite insightful in the sense. So let's have a simple demo of linear regression in TensorFlow. So yeah. So as I said, we had like is it visible? Okay. So we have some input data, x and y, which is like an output function that I have. And let's say for the sake of simplicity, I have this form. Y equals to x into 0.1 plus 0.3. So w is 0.1 and x is 0.3. So what I actually want my neural network is to find out what are these values, w and x, given some random values of x. And I just feed the same thing. So I have a w, which is the weight vector, which is again a random uniform vector, which is between -1 and 1. A bias vector of like zeros, and then this is my input function, that is wx plus b. So I'm trying to do a linear regression, so I want to minimize the loss. The loss is the squared error loss, if you know about it. And the optimizer that I use is like the classical gradient descent optimizer. So for training, when I want to train it, so right now it's only initializing. We just initialize it. So we have an optimizer object, and we do a minimize. We want to minimize the squared errors at each step that we have. There is this thing called init, where we try to initialize all these variables. These initializer variables actually initialize our w and b, which are like starting our variables that we had. And then we start a TensorFlow session. We start with a run function, as I said, with init. So all the initialization happens now. So until this thing, we just define it, and at this point, we actually initialize it. Then we try to do an iteration way of learning of how to get to it. So we say, okay, let's iterate to 200, and I want to train this. So I want to do this training function, which is minimizing the loss of the squared errors using this gradient descent. And at every 20 steps, I actually want to print it. So if we see it, which is like, so there you go. So it's pretty quick. Okay. So if you see this, we started with like some random values of w and x. Remember what we had in here? We had w as 0.1 and x as b as 0.3, and that is what we want in the end. So we start with some random value of w, that is 1.18, and some again random value in the distribution of the bias, 0.347. And then there are these several iterations after every 20 steps. It actually prints what happens. So it tries to minimize the overall squared loss. And if you see around 20th, it tries to converge it. So we have like w equals to 0.1. It's right able to come up with this. And x, the bias itself, is like quite close to 3.299. So that's how it actually works. So this is like a very simple example to just see how linear regression works. The next example that we have is word2vec. How many people know about word2vec? Or know about what word embeddings are? Okay, so in general, word embeddings are they're pretty nice concept which was introduced first. It was introduced before, but like the first major release that was word2vec was by Mykolov. There was another release, it's called Polyglot as well, which was like an earlier paper. But anyway, Mykolov's release, which was while he was working at Google, was given a word, just give me an n-dimensional vector of that word. What that vector particularly signifies, say if there is a word, say box, and there's like a floats with like 100 floats array, which like a one-dimensional vector, or like a 100-dimensional vector, you can actually say that that box is dependent on like what is the context of that particular word. So the neural network actually learns a language model where we actually can see, okay, given this context, say the box is on the mat. So given this context, what should be the vector of the word? There's a complex mathematical way to do it. Probably I'll try to explain that in the code itself, but here it is. So again, I have done this part, that's the downloading part. So we have to download a data set. So it's like an unsupervised language modeling scheme. So given all the words in the corpus, or all the words that we have, what we want to know is what are the vector representations of those words in that corpus. So first we download a data set, which is like the same data set that the paper used in Word2Vec by Matt Mahoney. Again, we have some called reading the data, building the data set itself, and we generate a batch. So the batch is something like, he introduces two different particular models, skipgram and continuous bag of words. So skipgram is something, say, you have a sentence, the cat sits on the mat. So sits on the mat, if you just say one particular phrase, then given the mat, give me the context word, or what is the word before it, or what is the word after it. And you just do a window over the entire sentence, and you just try to learn information from it. So given that, what we need is like, if the next word in a given phrase is X, what is the preceding word, or what is the probability of this? And if there is a particular nice sentence, which is a correct sentence, the probability is 1. If we just have like a noisy sentence, like a word from somewhere, two words from somewhere, which will never correspond to one another, the probability will be 0. So that's what the main learning is all about. So again, given we have a batch size, an embedding size. Embedding size is actually the n-dimensional vector. And we have like a skip window, which is like how many characters or words to skip. This is done on words, by the way. And then there is what is a valid window, what are valid examples. And then again, you started like a graph initialization, which is like the default graph that you have. TensorFlow actually allows you to have more than one graph. Most of the computations that I have done is like which only use like one graph. Again, there are these training inputs, these placeholders variables, training labels, the valid data set. Again, you try to run it on a device. There are certain functions for this particular example which were not coded for GPUs at that moment, even now. So it uses this device CPU. So this particular kernel runs on the CPU. This line means this. And then you have a TensorFlow variable. So your embedding is like for each word that you have, whatever the vectors that you have, you just try to not store them separately, but store them in like one singular array. And it's done because it's quite performance. It gives you a good performance optimization. And again, given the vocabulary side, number of words that you have, and the embedding sides, so given the number of words and what dimension of vectors you want, you can create an X by Y sort of a array. And again, you want to initialize them uniformly, and then you can just create a lookup. So given that word, just give me the vector. Then there's something called noise contrastive estimation. That's a weight that the actual, so they use something called truncated normal. And again, vocabulary size and embedding size is the same. So use the same embeddings as an input, but try to reduce this embedding size as the square root of the embedding size. And the biases is a simple 0 vector. So again, we define the same weight and biases. And the loss is a reduced mean, which we want to like reduce. And we want to particularly reduce this NCE loss, which takes in the input of weights, biases, embeddings, and training labels. And the samples that we have are also dependent on that. The optimizer, again, is gradient descent optimizer, with which we want to just minimize the loss on. So we can just define it in one line. Again, if you want to do, what do we really want to do is like, since a word is defined by its vector, what we really want to do as like, say, how does it really perform, is we want to find out which is the closest word. So if there is a word or an alphabet, like say A, what should be the closest alphabet to it? Like it should be some alphabet or not a word. So these sort of things that we'll actually see. And we have something called normalized embeddings. Like we just normalize these vectors, say between 0 and Again, it's the same lookup. And then we have a similarity. So we can do a cosine similarity or something. Now comes the part where we actually train it. So we have number of steps as, say, 100,000. And then we have a TensorFlow session. We initialize that. Again, this with session, so it follows the same thing. So as soon as the computation finishes, the session gets closed. You can actually like just have the session.extend to extend a new session so if you want more information. Again, for the number of steps, we iterate the loop. We generate a batch. So we take the data, read the input in a batch, and then feed. This feed dict is actually the dict which provides you the input and whatever the outputs are. And again, we provide the session run, which actually runs the whole computation. So far, we just initialized it. And at the end, we have this average dodge, which we want to just add upon. And each step, what we do is like we give the nearest neighbors of this word, and we want to see how it's performing. So at the end, we'll see a good visualization of these words. So let's start that. So here it's starting. By the way, the model runs like, if you complete the model, it takes a long time. So I have run it once, but I still want to show you what happens. So this is what we want to see. So nearest to the word from, in the first iteration, we get something like the sleigh, modernist, rain. And what we actually want is like these things to converge to some meaningful words. By meaningful, we'll just know in a moment. So as at each step, it actually tries to reduce this loss. From initially, we had 286. Now at 6,000 iterations, we have like 33. So as soon as we reduce it, we'll see some improvement in the kind of vectors that are learned. So we'll just see it in a moment. Yeah, so there you can see it. So if you can see, just see this nearest to is. So we have like things like was, as, has. There are some words which are still not like really close to it, but it shows the same form of the word is itself. Or like if there was some event or there is some event. So it comes in the same context. So the system is actually just learning it inherently. So this is the word typical algorithm itself. So I'll probably cancel this. So it like does a pretty good job at the end. So if you look at what the final embeddings that are learned are these embeddings. So if you just look at, so what we have done is like we have reduced those 100-dimensional vectors onto some 2-dimensional plane and just plotted those vectors. So the way we do dimensionality reduction is using TSNE, which people know about probably. It's again using some sort of a PCA sort of thing, but it does pretty good. Like it does this dimensionality reduction of higher dimensional vectors pretty easily. So just look at the top one. If you just see the letters, they actually come quite close to one another. If you see the word, this thing, president, in 2D plane, you can have this George, Press, William, which probably are presidents in America, and they come pretty like close to one another. The other example is here. Say if you want to see directions, if you just look at this part, you have like north, west, south, central, east, much closer to one another than others. So the way we can actually use it, so given the word vector that you have, what you can actually do is simply learn those embeddings, and you can actually get synonyms out of it, or like say antonyms out of it, which are pretty useful in like several contexts. Or just if you know them as initial weights of your, say, recurrent neural network or an LSTM, which is like more complicated deep learning for language, you can initialize your vectors or your, say, right now I did a uniform initialization. You can do like a much better initialization where you have some information about the data itself. And that's pretty insightful, and you get some good results out of it. So that was visualizing word embedding. So as we have mentioned, like it's not as fast as the other frameworks are. And there was a study which was made like by Soumit Chintala from Facebook AI Research. This is done on TensorFlow 0.6. which actually clearly suggests like for say AlexNet or OxfordNet, for that particular data set, when we are running connets specifically, that particular algorithm, the Nirvana runs or CUDNNs